Imagine standing at a checkout counter. You and your friend both order a 3-topping pizza, but when the receipts print, yours costs $15 and theirs is $22. How is that possible? When things seem random, we naturally try to find a pattern. But how can we actually measure, mathematically, if we can predict what something is going to cost? To answer that, let's start somewhere simple: Sam's Pizzeria. Sam runs a very strict shop. A plain cheese pizza is exactly $10, and every single topping you add is exactly $1, no exceptions. This graph shows exactly how Sam's pricing works. A straight upward line maps the number of toppings to the total cost. Notice how every single dot lands dead center on our prediction line. 3 toppings is $13 every time. Statisticians have a specific tool to measure this kind of accuracy. It's called the coefficient of determination, but most people just call it R². Think of that as a grading scale from 0 to 100%. Because Sam's pricing is perfectly predictable, his R² score is a perfect 1.00. In a strictly controlled system like this, knowing just one single detail, the number of toppings, gives you total power to predict the final bill. But stepping outside of Sam's shop, the real world rarely follows rules that perfectly. Take Ella's artisanal pizza down the street. Her base pizza is also $10, but her toppings are all over the place. A scoop of corn might be $1, while imported prosciutto is $3. If we try to predict our bill at Ella's using the old method, just counting how many toppings we ordered, our math starts to fall short. Looking at a chart of Ella's sales, the dots don't form a neat line anymore. They scatter. You might order 3 toppings and pay $13, or you might pay almost $20. When an environment has hidden complications, a single piece of data is no longer enough to guarantee an accurate prediction. Take a close look at the physical spaces between our predicted line and where the actual pizzas landed on the chart. These vertical gaps have a name: residuals. A residual is just the visual measurement of how wrong our guess was. It is the exact difference between our mathematical prediction and reality. Because of all these misses, Ella's pricing model earns a much lower R² score. It drops to 0.70. What does that 0.70 actually mean for us? It means that simply knowing the number of toppings correctly explains 70% of the total price swings at Ella's. A lower R² score doesn't mean the math is failing. It is actually doing exactly what it's supposed to do, telling us exactly how much of the price variation we've mathematically accounted for. But that leaves us with an obvious question. If our model explains 70% of the changing prices, what is causing the remaining 30%? This slide points to the culprit: unexplained variance. This happens because of a lurking variable we forgot to measure. For Ella's shop, the missing detail is the topping category. Because she charges $1, $2, or $3, identical topping counts lead to very different bills. To capture that final 30%, we have to move past our basic line graph. We need to build a more comprehensive model that tracks both the quantity of the toppings and their premium status. Scientists, economists, and data analysts apply this same math every day to determine if their models are trustworthy enough to use. This table shows how different fields interpret these scores. In a physics laboratory, researchers expect an R² close to 1.00. In financial markets, 0.70 is considered strong. And in studies tracking human behavior, an R² under 0.30 is normal. Humans are messy. Ultimately, the coefficient of determination acts as a universal confidence meter. It sits alongside every data chart, quietly warning you how much you should trust the trend line you're looking at. The smartest approach to data isn't pretending you have a perfect formula for everything. It's having the ability to mathematically prove exactly how much you still don't know.